we began by explaining what algebraic schemes for a base field. So affine locally, they are spec of a K algebra, which is finitely generated as an algebra. Morphisms between them come locally from K homomorphisms between K algebras. Then we talked of Chow groups, which to any algebraic scheme associate a graded abelian group, and its components are 0 on the negative side and are 0 beyond the dimension, etc., etc. We saw some properties. Then we wanted to set up Chow groups, and for that we began with closed subvarieties and their generic points. Closed subvarieties define the primitive cycles which are going to generate cycles for Chow homology. On these cycles, there is going to be some equivalence which is going to come from wild divisors. So this was talking about closed subvarieties in terms of their generic points. Then we talked about algebraic cycles on a scheme as formal linear combinations of closed subvarieties, always finite. And then we started making progress towards defining rational equivalence. As the first step, we said that if you have variety itself and on that there is a rational function, then what is the divisor associated to it? For that, we needed the notion of order of vanishing. We began by recalling the notion of order of vanishing in complex analysis. Then we said exactly that same algebra works for discrete valuation rings. And then if you are willing to forego the valuation property that what happens to the sum of two elements and only have the multiplicativity converting into addition, then you can also go to Noetherian local domains and define everything in terms of length. And so we defined order of vanishing for one-dimensional Noetherian local domains. And then if I have variety and a codimension 1 subvariety, then the local ring at the generic point of that closed subvariety is a one-dimensional Noetherian local ring, which is a domain because we began with a variety. And then applying this there, we can talk of the order of 0 or pole along a codimension 1 subvariety. This is where I asked you the question that if I have y minus x square and I have the x-axis, what is order of vanishing? And this we are going to discuss in the this discussion hour which is coming on. And so this allowed us to define the wild divisor of a rational function on a variety. But this definition of wild divisor only applied to dimension 1 less. Because if I have a rational function on a variety, then its vanishing or pole are along codimension 1 subvarieties. So what about defining equivalence in other dimensions? So we brought on various different closed subvarieties and rational functions on them, which are of one dimension more than the cycle in which you are interested. And for such a thing, you take the corresponding wild divisor and the sum of those, if that is what is rationally equivalent to 0. Then we define finally Chow group, saying this rational equivalent to 0, which is a subgroup, take the free abelian group of all cycles and go modulo this rat n on Zn, Znx mod rat n was the Chow group. Along the way, we also talked about taking these points on an open subscheme, complementary closed subscheme, and the projection and how this is a sheaf, etc. Yeah, so this is what we did in the morning. Alright, so let's go to what I am going to talk now. So now I am going to talk about how Chow groups are related to dimension, which had broached the subject. Now we will see that the Chow groups that we had defined indeed satisfy those properties. And then we'll begin looking at examples, Chow group of an affine line. Then we'll talk of Chow groups of projective line. We eventually want to talk of Chow groups of projective space. Today Amit talked to you about Chow groups of homology groups of projective space and how important those are for Chern classes. So we want to do it with Chow groups. But that will come almost at the end of the 6th lecture. It requires all kinds of stuff before you can rigorously prove the result. The answer is exactly what he said for singular homology. But the proof takes some doing. But right now we can do it for projective line. After that we will talk of the degree of a proper surjective morphism of varieties. You see, we are interested not just in one variety at a time, but what happens when you have morphisms. That's of greatest interest. So morphisms between varieties have some kind of degree. What is this degree? If two things are of the same dimension, think of oriented manifolds. So I have two oriented manifolds and a map. Imagine a proper map. What does proper mean? Proper means inverse image of a compact is compact. That's what proper means. Okay. This variety goes and wraps around that variety a certain number of times, generically. Over a general point, there are so many inverse images. That is the degree. There are some exceptional points where the fiber may even be positive dimensional. Yeah? So you leave out those, or sometimes you have to count the fiber with multiplicity. In topology, you will see it. So, but you have the notion of degree in topology, one space mapping to another. So here's an exercise for those of you who have not seen. Think of a football, think of a torus, give a map from torus to football of degree 2. Okay. So most of the points, this is an orientation preserving map everywhere, might have some singular points, and mostly over a point there are 2 points. This is very important in the theory of elliptic curves. You might have seen it in such a context. A 2-sheeted cover, elliptic curve has a 2-sheeted cover of P1. There are lots of curves which have 2-sheeted cover of P1. Those are called hyperelliptic curves. You might have heard such names. Anyway, so that's the notion of degree. This degree, which I just now gave a set theoretic / topological, basically set theoretic explanation, has also explanations in terms of homology, in terms of algebraic degree of polynomials, and all those degrees match if properly defined. So we are going to talk of degree of a proper map. And what happens in unequal dimensions? Then the degree is defined to be 0. Okay. All right. So this degree is something which is going to help us define proper push forward of cycles. So our cycle generated by primitive cycles which correspond to closed subvarieties in an algebraic scheme X, and there's an algebraic scheme Y, and there's a morphism over K. And each variety has an image there, and because this is a proper map, the image of a closed subvariety is what? Closed. Now you make it a variety by giving it the reduced induced scheme structure. It is irreducible because it's the image of something. So therefore it's a variety. So image of a variety is variety. So if I have a cycle, you may think naively that all that I have to do is to take its image cycle and define it to be the image of cycles. No, you have to put the degree on it. You should think about it, why we are going to put degree on it. This is a question for a discussion hour that you are going to think about. You have to question every definition. Why do we so define it? I'll give some analogies, but finally you have to persuade yourself that this definition is good. Ultimate test is whether these definitions lead to interesting theorems which don't refer to these definitions. Okay? And all this has passed these tests, which is why we are talking about it here. So to a certain extent, you should have the attitude of, oh, let me for the time take it on faith that this is useful, master the technicalities, and then revisit it and see why this is defined like this and how does it help. Okay? All right. And not wait, saying, motivate everything to me fully before I take the next step. No, you should be able to take the next step also, while keeping in mind that I am still going to question why that was done. We have defined push forward for cycles in terms of proper map, image, degree. But if it is to define something on Chow groups, you will need to know what happens to rational equivalence under this push forward. Only then going modulo in the domain will correspond to going modulo in the codomain, and the map on cycles will descend to a map on Chow groups. So the important job is to do whatever you are doing on cycles gives you something well defined from rationally equivalent to 0 to rationally equivalent to 0. This is the major effort in my 6 lectures is going to be. So we'll begin that by talking about push forward of an individual wild divisor itself, and then talk about what happens when you have a cycle and whatnot. So let me remind you how we have defined. We had a scheme and we had the group of algebraic cycles rationally equivalent to 0. We went modulo this and arrived at this. And now we want to check that the properties on slide 1.2 are satisfied. So let's go to slide 1.2 and check whether the properties are satisfied. So yes, this is what we have done. We have defined a Z-graded group and called, there is nothing to verify here, this is just the definition, it is called that, very good. And this is true because there are no negative dimensional varieties, so there are no cycles, and so the quotient is 0. Also, any subvariety is of dimension at most equal to the dimension of the variety. So beyond it they are 0, so we have verified this. Now, if a scheme is non-zero, non-empty, then it has at least some point in it, okay, and some subvariety, and it has some dimension. So take its irreducible components. If you take an irreducible component, that's a cycle, that's a closed subvariety. Can it be rationally equivalent to 0? For that you will need a variety of one dimension more inside there and a rational function on it, whose divisor is this. But if you have taken an irreducible component, take one of highest dimension if you want. Actually, it doesn't matter for this. And then there's nothing higher of which this can be the wild divisor. So this will be not equal to 0. So what will happen is the Chow group ends up being non-zero the minute your scheme is non-empty. On the other hand, if your scheme is empty, then the set of subvarieties is empty, and so the group on it is 0, and so on. So we have verified this. Which one? This. And for the base field, let's verify this quickly. Spec K. What closed subvarieties does spec K have? Just spec K. There is nothing else. And so there is only one cycle, and so the group generated by it is Z. And there is nothing higher. So it's not going to be boundary. No multiple of it is going to be boundary. So it's going to be the free abelian group on this. Because a single generator, you can just call it free group if you want. And so that's the answer. And higher ones are 0 because there are no subvarieties of higher dimension. Then look at this. If it has C irreducible components, look at the subvariety generated by that. There is no possible linear relationship between them either, because that means there is a D plus 1 dimensional variety or number of D plus 1 dimensional varieties and rational functions on them whose wild divisors add up to that. There are no D plus 1 dimensional subvarieties there because D is the highest dimension. And so all of those different D-dimensional components, and irreducible algebraic scheme may have irreducible components of smaller dimension also. But the D-dimensional components, those are going to generate cycles, those are going to be linearly independent. And so the top homology, Chow homology, is going to be this. This association we want to know is functorial. So suppose I take an isomorphism of over K of a variety X with a variety Y. Then closed subvarieties here exactly correspond to closed subvarieties there and are mapped there. And rational functions correspond to rational functions under this isomorphism, etc. So you get an isomorphism between those Chow groups, which is clearly functorial. So the Chow groups are functorial with respect to isomorphisms at the least. Their functorial properties with respect to will be addressed later. Yes, nothing to verify here. That you can verify after this course is done whether it was already nothing mathematical here. It's just a promise I'm making to you. Okay, so coming back to 2.1, or rather the last thing here. Exercise, check the properties stated in slide 1.2. We have done that. And so here some of those are recalled again. Now as promised, let's look at an affine line. We already determined the Chow group of a single point. What are zero-dimensional varieties, by the way? Over K. Abhishek? Variety. Now, what are zero-dimensional variety over K? No? Oh, what in algebraic geometric terms? What are they?
Points.
What point? Spec of K. That's it. Yeah. Any advance on spec of K? Finite extensions of K. Absolutely. So you might have finite extension of K and a finite extension field, because remember, these are algebraic schemes, they are finite type over the base. So you take a finite extension of K and take its spec. That's also a zero-dimensional variety. So spec C is a zero-dimensional variety or spec R. Okay, that. So for that also you can decide what are the Chow groups. And same argument is going to apply to spec F. Spec F, where F is a finite extension of K, okay, finite extension, same answer is going to come, yeah, because this itself is the basic cycle, it has nothing sub in it, and there is nothing larger dimensional, exactly the same argument holds. So now let's talk of, we have disposed of the zero-dimensional case completely. Now let's look at the simplest one-dimensional case where you have an affine line. So how many irreducible components does it have? It's a variety. It has one irreducible component. That's our dimension 1. So we already know what its top Chow homology. It's free abelian group on the number of irreducible. So that's Z. So now let's look at Z0A1. Okay. So what is Z0A1? So it's generated by points. Earlier we said if the point is P on the real line, then take x minus P. That rational function has a wild divisor, that point P. But now remember, our field K is not algebraically closed. So you may have a point which is not defined by a linear polynomial, like x minus P, because P is not in your base field. Okay. So what are the points on this affine line? They correspond to what? Maximal ideals. Maximal ideals in polynomial ring in one variable, what are they? What are maximal ideals in KT? KT is what kind of a ring? PID. So all ideals are of the form generated by a single generator. But if it is to be a maximal ideal, what do you require of that polynomial? Irreducible polynomial, yeah? So you take an irreducible polynomial, it has a certain degree, and it will define a field. That field is KT mod FT. In your field theory, you have studied that. That's the residue field at that point, KT mod FT. Yeah? And that has a certain degree, it's not degree 0. And that degree of this extension is the degree of the polynomial. Okay? Now, if I take such a point, which is actually spec F, spec capital F, where capital F is KT mod FT. Okay? I have that point there, KT mod FT, where FT is an irreducible polynomial of degree D, which is greater than or equal to 1. Then, is there a rational function whose wild divisor is exactly this point P? So I have some point P belonging to spec KT, and this P corresponds to FT. Okay? So I take this P, and that is the wild divisor of what? Any candidate? Something which will give point P correctly. That is F. F exactly vanishes there. The wild divisor of this polynomial Ft is P. That's exactly where it vanishes. With multiplicity 1. Okay? So, I have given you the definitions of what is the vanishing multiplicity of something, order of vanishing. So, here's my simple question to you, that I have an irreducible polynomial Ft in a field, and it vanishes somewhere at a point P. Obviously, P is not K valued, but it's a closed point. And I'm asking you, what is the order of vanishing of this polynomial at that point? What is it? The order is 1, isn't it? It vanishes there once. Okay? Very good. Remember that. Because somewhere you want to think of this as having degree D as its weight. That's the degree of this point over the base field. But the vanishing of Ft there is single vanishing. This is all very simple algebra, just definitions. Polynomial ring in one variable is what you study in school basically. So these definitions are reduced to something that you have known from roughly 8th standard onwards. 5th, 6th, 7th, they do integers. And at least 50 years ago when I was in school, 5th, 6th, 7th was integers. And 8th, 9th, 10th was polynomials in one variable. And the same methods were applied again. Euclid and algorithm. HCF, LCM, all kinds of same things were done all over again. And then in 11th standard, there were polynomials in several variables, and which immediately became more complicated. You had to eliminate something, and sometimes they had symmetry, cyclic polynomials. Chakriya Padavali was what it was called in my classroom. Okay, but back to this. This is all very simple high school algebra. So this is the divisor. So as a result, this P, therefore, belongs to rat 0A1. This is the wild divisor of a rational function. Okay? In other words, this is equivalent to 0 in A0A1. Let me write equal to, now the same notation square bracket has become its class. Here it is cycle. If I want to say cycle, I'll say cycle equivalent to 0. If I want to say class, I'll write class equal to 0. Okay? I'll use either notation by context to decide whether I am talking of class or cycle. And sometimes you can only talk of classes and not of cycles. The more complicated constructions are going to produce classes without any well-defined particular cycle. This you will increasingly see in Amit's lectures even in the coming 1 or 2 days. Okay. Sometimes not even a class but an operator. Operator on chow, as you will introduce Chun classes in the beginning, yeah, as operators. Okay. So we have done this, that therefore anything, all its generators are equal to 0, and that tells me that this is therefore equal to 0 because the free abelian group on such things, and each one of them is equivalent to 0, so this becomes 0. Okay. So we have arrived at the determination that A1 equal to Z generated by A1 and A0 A1 equal to 0. So we have done this job. Okay. Yeah, so all of this is done. While divisor of F is equal to this. This is what was written here. So we are done with this slide. Any questions on this slide? I think it's pretty clear, yeah? Quite elementary actually. This is just, you have to just go on, you have to basically memorize the definitions in the beginning and then it will become habit like with all definitions. So do that. So now instead of A1, let us talk of AN. So what is AN? AN is the spec of polynomial ring in n variables. So from 8, 9, 10 standard, this has suddenly become 11 standard. But after my days in school, everything was made more advanced. So instead of 11 standard school, it became 10 standard and then you go to junior college and whatnot, yeah? And so probably your generation, does it continue up to 10th? Yeah? So multivariate polynomials are already in 10th standard or perhaps? No. Then when are they? 11th standard. Yeah, those who went to college recently tell me, when do you first encounter multivariate polynomials?
Factorization of x squared plus x squared plus something y squared, so that is multivariate.
Okay. So you are after all exposed to it, but not in a very systematic manner. But in college you studied it, and in MSc you studied it, and all the time now you know it very well. Okay. So now we are going to look at this polynomial ring in these many variables. So we already know what is the top Chow homology. What's the generator there? AN itself, and it cannot be equivalent to 0 because there is no higher dimensional variety. Now let's look at all these others. Now beyond dimension it is 0, that we already know. Now what about A0? So here a simple trick. Suppose you take a point P in AN. Okay, it's defined by some maximum ideal. Now you take a line through that point. This point lies on a line. Is that clear? Little exercise. Take any closed point in AN and then there's a line which passes through this point. Okay? A line which is defined over K, call it A1 over K, you will have such a line and that point will lie on such a line. Prove it. Once you do that, now this point is rationally equivalent to 0 because that line is a closed-up variety and on that there is a rational function, actually a regular function, whose divisor is that point. 0th Chow group is going to be 0. Top Chow group is going to be Z. In between we don't know yet. So as these lectures advance, probably in the last lecture we'll be able to prove that all in between are 0. Okay. Alright. So yeah, it says here, slide 6.9. That's the 6th lecture, almost to the end. We'll prove that all in between are 0. But it's important to keep this example in mind. You get a feeling for Chow groups by knowing how they look in spaces with which you're already familiar. Yeah.
So to make a line pass through a closed point, I mean, it could be, let's say, some characteristic P, let's say, not singly generated. Then if it were characteristic 0, then primitive extension 0 you would get.
So you think it is true? There is such a one? You want to discuss it in the tutorial, whether there is a line passing through? Yeah? Okay. Alright. We'll do that. A spec of Ft. You can take, you might have to go to spec of Ft instead of spec of Kt. for that line. Okay? But that equally serves the purpose. Okay. So, where what? I have said you can have, where is it? Yes, second point. So, what he is saying, he is doubting whether it is defined over K. So, I said discussion hour. And suppose it was not defined over K, how will the proof go? Same way, no difference. Some A1 over what? Right now says nothing. Discussion hour, prove or disprove, you can choose it over K, but it will make no difference to the answer. This you should understand now. Okay? But you see, here's a very simple question that given an and a close point in it, is there a line through it defined over K? Simple question, no? Nothing to do with this advanced instructional workshop. So this is the kind of thing I want you to settle instead of my answering fully. So that in the discussion hour. Okay, remember this and raise this point when whosoever is here. Okay. So now let's look at Chow groups of a projective line. So what Chow groups are there going to be for projective line? There is going to be Chow 0 and Chow 1. Nothing beyond, because that's beyond the dimension. Below it's anyway 0. So what's going to be the first Chow group? This is a variety of dimension 1. So its first Chow group is going to be Z generated by P1. So only question is, what is it? 0th Chow group. So for this I want to introduce the notion of a degree of a point on this P1. Define that degree to be the degree of the residue field of that point over the base field. So every point in P1 has a degree, like every point in A1 has a degree. Every close point on an algebraic scheme has a degree, because it's an algebraic scheme, that close point is finite over the base, so it's a finite extension, its residue field, and its degree is the degree of that point. So every point of P1 has a degree, and my claim is this degree gives you an isomorphism from the 0th Chow group of P1 to Z. And generator, therefore, a close point of degree 1. Are there close points of degree 1 on P1? Yeah, there are at least how many such? 3. 0, 1 and infinity are there. So there are close points of degree 1 there. So pick one of them, the 0th one or infinity 1. Infinity 1 is good to pick because the remaining is your standard affine line. You pick anything else, that is also an affine line, but you will have to write the coordinate in a convoluted manner. Especially if you remove the point 1, then for the remaining you will have to do a bit of algebra. Okay? So P1 is like Riemann sphere, one copy of C and extra infinity. Easiest visualization for this algebraic purpose. So every point has a degree, and that degree is going to give an isomorphism. So what will it involve saying? It involves saying that 2 points, the classes, well, suppose I have degree, I'll compare everything with this point at infinity. Instead of comparing 2 with each other, I'll compare each one with a standard one. So my infinity one is my measuring rod, and I compare anything with that instead of comparing 2 things with each other. So I don't say that, oh, this breadth is this much times this one, and that chair is this much times this chalk. I say this is so many centimeters, that's so many centimeters. Centimeter is my standard. So this infinity point and its cycle are my standard one. They are the generators. So then my claim is everything else of degree d is rationally equivalent to d times that point at infinity. How do you verify that? So given any other point, you have to show, if I take this f, which vanishes here, degree d point, how much does this vanish at infinity? At infinity, if I have polynomial ft, if you are more used to complex analysis, think of you have polynomial fz on your Riemann sphere. And this fz has a pole at infinity. Yeah? Any polynomial has a pole at infinity. What's the order of the pole at infinity for a polynomial? The degree of the polynomial. Okay. So the infinity is going to produce degree times x infinity. So as a result, so if that point at infinity is p infinity belonging to p1 and have some other point p in a1 which is p1 minus p infinity, and suppose the degree of this is d, then I produce this rational function which vanishes here exactly once, but then it vanishes at infinity d times, and therefore the wild divisor of this f on p1, this was only happening on a1, but if I do it on p1 I have to also look at the pole, and that is going to be p minus d times p infinity. Okay, and this is equivalent to 0. So when I go modulo rational equivalence classes, that means p is equal to d p infinity. Look at this equation and this equation. Now, why are both of them true? Because the square bracket means something else in them. Here they mean cycles, here they mean classes. So this class is d times this class. So this generates. Now can I have this p infinity itself as divisor of a rational function? No, because one of the important properties is if I take any rational function on this Riemann sphere, the number of zeros counting multiplicities is equal to number of poles counting multiplicities. Overall it is 0. So you cannot have something which has exactly one zero or pole at p infinity and nothing else. So that thing is non-zero. No multiple of it is 0. You cannot have a rational function whose only 0 is a single point with a certain multiplicity, because it will have some equal order poles somewhere else adding up to that same number. Okay? So this not just generates, but it's a free generator. No multiple of it is going to be 0. So as a result, we have proved, well, I had called this exercise, but you know, it's still an exercise if you solve it again. You know, the exercise is called pull-ups, push-ups. Yeah? How many times do you do that? Or you say, oh, I did once pull-up. But exercise means you do it again and again. And so this is very important with all exercises in important mathematics textbooks, that you have to do them again and again. Only then they give you exercise. You do it once, then the effect goes away. Okay? You have to do maintenance work on your mathematical knowledge. Just as somebody who is a bodybuilder has to do maintenance work on his muscles even after he builds them by repeating the exercises, increasing the difficulty incrementally and so on. So even when you study something, you have to revisit and solve it again and solve it again and solve it again. And then you begin to see connections also. Next time your solution improves. So keep doing the exercises again and again. I have told you the solution, but you also now solve the exercise by yourself again after a few days, again after a few days. Okay. This I have given the details which I want you to do as exercise. What I rapidly said here is written in painful detail there. Don't read it. Try doing it, get stuck, and then look at it. Then start all over again, and again get stuck, then again look at it. And keep doing it till without getting stuck you can do it fully. Then once again do the whole thing. Rinse and repeat. Yeah? Till these things you understand. You see, in this I like to tell all my classes whenever I teach. You know, in music there is riyaz, right? The same taan, the same palta, the same sargam. You have to keep doing and doing and doing till it comes exactly right. Okay? You begin to hear your tanpura exactly correctly. In the beginning you can't even hear the tanpura. But then you start hearing, then you, oh, this is off, adjust this slightly. And then, yeah, this note is right, hold it there. And then you keep doing it, different speeds, different combinations. And that's called riyaz. Where does that word come from? Riyaz means mathematics in Farsi. I know this because I worked in Iran for some time and I was called Ustad-e-Riyazi, professor of mathematics. Okay, so you have to do riyaz of this stuff all the time, and it's enjoyable, believe me. This repetition is very enjoyable. That is what will sustain you. When you like something, you like singing it again and again. So when you are under your shower, you might sing your favorite song, or you might go through the proof of the chow group of something. Yeah? Very good. All right. So now, any questions on this? Or should I go to the next slide? ठीक है क्या? I'll let you stare at it. Okay, let's go to the next slide. And I am ahead of time. I am very comfortably placed in this lecture as usual, because I have saved enormous time by preparing the slides in advance and sending you copies. So you can pay attention, you lose nothing, you are not busy scribbling. Okay? But later you go back and read these slides again. Riyaz. Riyaz also means you go through the lecture. In the evening, you go through all these lectures again, looking at the slides, looking at the notes you have taken of speakers. So tomorrow when you come, you are ready to go further. Soon this is going to pile up. And if you don't do this amount of homework every evening, then it becomes tough to keep up with what's going on. So now we are going to talk of the degree of a proper surjective morphism of varieties. If it's a proper morphism and surjective, so if they have the same dimension, then such a morphism is generically finite. A proper morphism of the same dimensional varieties is generically finite. This statement, nothing to do with Chow groups, is that kind of statement which is elementary algebraic geometry, and you have to challenge yourself to be able to prove it. That if I have proper surjective morphism of algebraic varieties of the same dimension, then it's generically finite. Okay? There might be some exceptional points where it's higher dimensional. Fiber can't be discrete infinite, no chance. Because inverse image of compact is compact, remember, in topological terms. But there could be positive dimensional fibers. Can you give me an example of a proper surjective morphism of varieties of the same dimension, where suddenly some fiber is positive dimensional? No? Blow up. Very good. So blow up is an example where this happens. Yeah, proper surjective morphism of varieties, but one fiber is suddenly larger. But generically, what's the degree of the blow up? So degree 1. Okay. All right. So if I have two varieties, first of all, the very fact that it is surjective means the domain is of larger dimension than the codomain. You know, topologists were totally shocked out of their, first possible shock, when Peano gave the example of space filling curve. Okay? And that completely shook their understanding of dimension. This shouldn't happen. Reason was those functions which Peano produced were horrible functions of mechanics. They are not functions of geometry. And our intuition as mathematicians is for functions of geometry, not functions of mechanics. Okay? And so analysis has these really terrible functions. The problem was not with intuition. Problem was the definition of a continuous function is too liberal. And so really pathological things can be produced from continuous functions. But anyway, so your intuition is right there, and in thinking that dimension of the image is going to be less than or equal to the dimension of the codomain. In algebra, this is indeed correct. Prove this. So if I have surjective morphism of varieties, that codomain is of less than or equal to dimension of the domain. Nothing to do with proper also. Okay. So we must have this. And then this induces a morphism of fields. How does it induce a morphism of fields in the reverse direction? Yeah? What do you do? Stock at generic point. So the generic point is going to go to generic point. Why? Because this is surjective dense. Correct. So generic point is going to go to generic point. So at the stock level map in the reverse direction. And those are fields. So therefore any homomorphism means an extension of fields. There is no kernel possible once you have homomorphism of fields. Okay? So I have got a field extension in the reverse direction. And that field extension is finite if and only if these two dimensions are the same. This is what I am telling you all this time, right? Generically it is finite. In the last century, people used to talk generically also in the sense of in general. But once generic points were invented, many of those properties became synonymous with over the generic point. This is not completely synonymous, by the way. You should make trivial counterexamples to this. Okay, so this is the definition of degree of morphism in algebraic geometry. One possible definition is this degree is the degree of this extension field. But what if there is an inequality? What if the dimension of this is bigger than dimension of that? Then you declare the degree to be 0. So degree is really keeping track of what happens to the generating cycle, top cycle, in going from here to there. If the dimension there is less, then the image of this top cycle is lower dimensional. So it's not going to produce a top cycle at all. So this has disappeared when you go to the other side. So that's why you want the degree to be called 0 in such circumstances. So in this slide, we started comparing two varieties. Up to now, when we talked about Chow group, we talked about one variety at a time. Now we have come to comparing two things and what happens under a morphism. And for that, we took the example of a proper surjective morphism of varieties, not of algebraic schemes, of varieties, simple case. And then we defined degree in a field theoretic manner. I told you what degree intuitively means: wrapping things around, how many sheets, torus wrapped around sphere, elliptical, hyperelliptical, all such examples. We talked about degree in the sense of polynomial. So suppose I have P1 to P1. I have a map defined by a polynomial fz. Fz defines a map from P1 to P1. Infinity goes to infinity if fz is a polynomial. If I take a rational function fz upon gz, that also defines a map from P1 to P1, right? What's the degree of that morphism? So any definition you have to test it in some simple case. So I have a map from P1 to P1. On P1 my coordinate is z equal to infinity is the thing there. And my polynomial is z divided by z square minus 1. What's the degree of z upon z square minus 1? So here's for the exercise session. So I map f going from P1C to P1C. C is not relevant for this exercise. Z goes to z upon z square plus 1. What is degree of f? Okay, solve this. A simple definition. And check this degree is what it's doing to the top homology. This degree has something to do with the degree of those functions involved. And this degree is the degree of the rational function field extension. Also, this degree is the number of inverse images of a point in general. There will be exceptionally a smaller number. All these numbers will match. Check it with that example. And then prove it for a general rational function, P1 to P1. Do it first in this example. Okay, so that's what we did on this slide, and we are through with this slide. So any questions, or should we go ahead? No, go ahead. The exercise I have given you is very elementary, and you understood. Different manifestations of degree you are going to check are one and the same. In the simple example of Riemann sphere to Riemann sphere, morphism defined by a rational function. When is such a morphism surjective? At least tell me that. I have P1 to P1, a morphism defined by a rational function of z. Non-constant, exactly. When it's non-constant. But suppose I had P1k to P1k. What will then, when will it be surjective? What does non-constant mean now? Okay, if P1 is too difficult, take A1k to A1k. Give me a proper surjective map from A1k to A1k. Map being proper has nothing to do with whether the spaces themselves are compact. No? So yeah, so what's a proper surjective map from A1k to A1k? Defined by a polynomial. What are the morphisms? They are defined by polynomial. When does a polynomial define a surjective map? Once the polynomial is non-constant. Is that proper? Is that map proper? Yes. How will you prove it's proper? Wonderful. Restriction of the map from PV, because the inverse image of infinity is infinity and base change will give you proper. Yeah. So what is the degree of this proper surjective map? Degree of the polynomial. How many inverse images does a point have under a polynomial of degree f? How many roots does f have? So if I take ft equal to something, in general it has d roots. So generally there are those many points. Exceptionally it may have some things may come together, or higher degree point and so on. So I think now the degree of a morphism, the idea is clear. Let's go on to the next. So with this degree of a polynomial in hand, or degree of a morphism in hand, we are going to do a proper push forward on cycles. So remember, our idea of making Chow groups functorial is making cycles functorial first of all, and then asking whether with this functorial map from cycles to cycles associated with the morphism of algebraic schemes, whether rational equivalence is preserved or not. It becomes a question of preservation of rational equivalence once you have a nice definition of push forward or pull back on cycles. So let's take a proper morphism of schemes and some n, we are interested in nth Chow groups. So we want to do it first on cycles. So this is generated by n-dimensional closed subvariety is V. Corresponding generator is square bracket V. So you take its image, give it reduce-induced subscheme structure, and then it's a closed subvariety of Y. Why? Because it is irreducible. And the induced morphism V to W is proper and surjective. Okay? Why is it proper and surjective? Well, surjective it obviously is. Why is it proper? Is it base change? No. The inverse image of W might be something else. But whatever that is, that base change is proper and this thing is closed in it. Okay? So see, increasingly I'll use tiny algebraic geometric arguments tacitly without even thinking about it. But then you have to therefore attentively see, oh, why is this? And if you try reading Fulton's book, he makes huge jumps all the time, leaving all kinds of things to you without even stating them, and sometimes with no idea of how to prove it. Okay. So this is a proper morphism and surjective, and so it has a degree, and we define f low star V to be this degree times W. Because why? Because, well, think in terms of points. If I have morphism from V to W, same dimensional proper, and I have a point there, and I take its image, those 2 points will have different degrees. The residue fields may be different, so there is a residue field extension involved. So that is one point for a set theorist, but for us it's a point with a certain degree over the base field. And so when I push forward, I put that degree as a numerical multiplier on its image. So such an operation should be well behaved as much as possible with respect to flat deformations. All numerical things that we want, as far as possible, we want them to behave nicely with respect to flat deformations. Somebody was asking me such things in the morning. Okay. So if I move this point slightly in a flat family, this higher degree point will split into degree 1 points, how many of them, degree many of them. And now if I take their image, there are those many points below. So when I take the image of this first higher degree point, I have to multiply that by the degree. Okay. So I define this by this degree times this image. And if the dimension is actually less, then this we have already explained why we want it to be called 0. So we have finished defining it on the generators. Generators are of this kind, where V is a closed subvariety. And we have finished defining f low star on those. And now extend by Z linearity. There is a unique extension by Z linearity because it is a free abelian group. That is the universal property of a free abelian group over any set. That given any map, set theoretic map from this set into any abelian group, and it extends uniquely to a group homomorphism. factors through this. So what if I take the map X to spec K? I take a complete variety, then I have this map to spec K that is proper. That's the definition of a complete variety. Okay? That is what is compact in geometry. The word compact usually includes Hausdorff as used in geometry. Okay? But not in algebraic geometry. In algebraic geometry, we separate every cover has a finite subcover property from the geometric aspects of it. Those become proper, while the set topological aspects become quasi-compact. Okay. So suppose I have complete variety, so P to spec A is proper, that's what it means. Then I go from Z0x to Z0 spec K, because if I take a point here, its image is that point, same dimensional. So now what number do I give? That number is the degree of that point. So if I take any zero cycle on my algebraic scheme X, that zero cycle is a formal linear combination of points. Each point is of a certain degree, and the direct image is just the sum of those degrees with those coefficients. So such a thing defines for us a map degree from Z0x to Z in terms of the generator. Okay? And how will it behave on all other non-zero things? Because if I take a positive dimensional variety in X, its image is nevertheless only spec K, lower dimension. So I have to define it to be 0. So this was an example of how a proper push forward looks under the simplest possible map, namely the structure map of an algebraic scheme. Any algebraic scheme is a scheme together with a morphism to spec K. So what about that? Well, if it is proper, we define this, and the answer is this. But did we use that it is proper in defining this? No, because from any of those points to spec K, it's anyway proper. So properness of this was not used in defining degree of a zero cycle. Right? If the map is not proper, then this won't be well behaved with respect to rational equivalence. So on A1 you have various zero cycles of various different degrees, and they are equivalent to each other after all, because A0 of A1 is 0. So the degree is not preserved by rational equivalence. On P1 it is, that's what we talked about some time back. So this degree of a zero cycle can be defined on any algebraic scheme, not a very useful concept unless that scheme is proper over spec K. Okay? So we have defined this push forward on cycles. Let's look for its functorial properties. So if I have two different morphisms of varieties which are composable, so the domain of this codomain, and this codomain is the domain of the next, so I can compose them. And I take the composite. And suppose both of these are proper surjective, so they have degree. Proper surjective ensures that generic point goes to generic point. All that is required that it's dominant to make the generic point go to generic point. Surjectivity not important. Okay. But if it is proper and dominant, then it is surjective because the image is closed. Okay. So I will not go on saying dominant, dominant, dominant when it is proper. I'll simply say surjective. So now this degree multiplies, because when I have tower of field extensions, one extension and then extension, the combined extensions degree is the product of these degrees. Why? Somebody quickly machine gun the answer, fat, 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 fat. This is the kind of thing I mean, that you have to go back, challenge yourself on little things so the proofs are ready. Yeah, so how do you show that in a tower of fields the degree multiplies?
Explicitly will give the basis.
Correct. Correct. Very good. Very good. You can do it by giving explicit basis. Very good. So degree multiplies, and therefore if I have this composite, then the first one is going to send some primitive cycle to its image times this degree, and then image of the image times degree of that, but it was already carrying this coefficient, so because it's extended by linearity, product of the two coefficients, which is what will happen under the composite. So which is why this is equal to this. Clear? You want to write this and see that this is what is happening. Simple argument. Is this argument clear? Okay, I'll wait for a minute, those who want to write. You should not forget the habit of writing just because my slides are ready. So do this little scribbling for yourself and check that yes, indeed this is okay. So in this X, I take the class of something called V. And its image is going to be the class of V prime. And this V prime is going to go to V double prime. And so the image of V under composite map is V double prime. And then the image of this square bracket V is going to be degree V over V prime times square bracket V double prime. The image of square bracket V double prime is going to be degree of V prime by V double prime times square bracket V double prime. So the combined image of square bracket V is going to be degree V by V prime times degree V prime by V double prime times square bracket V double prime. But this coefficient is this, which is the degree of the composite map. So this is indeed has this property, but to be functorial, one more property has to be satisfied, that the identity isomorphism should give the identity map. Why does it do so? Because it leaves every cycle physically unaltered and induces a map from itself to itself, which is the identity, therefore it has degree 1. So therefore it simply ends up giving you the identity map on n cycles for any n. So to identity there is identity and to composite there is composite, therefore this is a functor. Yeah? And what happens under automorphisms of X or isomorphism of X to something? Well, the degree remains the same under this isomorphism. And because it's an isomorphism, the resulting map also is of degree 1 always. Okay? So all this is nicely functorial with respect to isomorphisms. This is one of the points people sometimes forget mentioning, but it is very important that under isomorphisms at least things have to behave well before more complicated kinds of maps. Okay, so hence the association X goes to Z star X and F goes to F star defines a covariant functor from the category of schemes and proper morphisms to the category of Z-graded abelian groups and homogeneous degree 0 homomorphisms. So we have proved the functoriality of cycles. We want to prove functoriality of Chow groups, but we have proved that of cycles. So let's go on. So if this functoriality on cycles is going to factor down to functoriality on Chow groups, which are quotients of cycles modulo rationally equivalent to 0 cycles, then the push forward has to take the rationally equivalent to 0 cycles in any dimension to rationally equivalent to 0 cycles in that dimension. Now the simplest rationally equivalent to 0 cycles are cycles in one dimension less than a variety, which are the Weil divisors of a rational function. So to begin with, and everything else is built of this. So we have to check how does push forward behave with respect to direct image of Weil divisors. So let's take that. So I have this proper and V is a closed subvariety of X, and I take a rational function and I take its Weil divisor. And we will show that under this to this one is rationally equivalent to 0. This is what we have to prove. It lies in rat n. And it will show that F low star maps rat nx into rat ny because rat nx is the linear combination of such principal divisors defined with respect to various n plus 1 dimensional closed subvarieties of X. Finitely many n plus 1 dimensional closed subvarieties of X and rational functions on them, non-zero, their Weil divisors, add them up. Let me ask you quickly, suppose I take a rational function on a variety and take another rational function on the same variety and add their Weil divisors. Is it the Weil divisor of something obvious? Product, exactly. So it will be because we said all the time that the order of vanishing of a rational function is additive with respect to multiplication. So when you write a rational equivalent to 0 cycle coming from one extra dimensional varieties and rational functions, you can assume those varieties are distinct. Because if there are two common ones, just multiply those rational functions together and simplify. And you don't need any numerical coefficient because absorb that numerical coefficient inside. If the numerical coefficient was 5, change the rational function to r to the power 5. If the numerical coefficient was minus 3, what do you do? 1 upon r cube. The numerical coefficients also come inside. You can always assume these are distinct varieties and no numerical coefficients apart from 1. Okay, so this is what we have to prove, that if I have this, then it will therefore induce a map here. So we have begun with V, and which is one dimension extra. We have taken a rational function, we have taken its y divisor, and we want to prove that this direct image is in this. Once we prove that, we have a well-defined map on the quotients. And because it was functorial on cycles, this will show that it is functorial on Chow groups. Only what was remaining to show it factors. But composite is composite on cycles, therefore through the factoring. Identity was identity on the cycles. So it's functorial. So functoriality falls off from the functoriality on cycles. And for cycles, F low star, we only used common sense algebraic geometry, the idea of degree, that's all. So this thing that it will take rational equivalent cycles to rational equivalent to 0 cycles was classically known. You see, a whole lot of algebraic geometry was classically known. All those Italians and people like Riemann and whatnot operated with their instinct and did the right things more often than not. Sometimes they did wrong things, but more often than not they did the right things, and they didn't have all the right definitions and the in-between steps. So these results won't surprise them if you explain it to them in language which they understand. They'll say, yeah, we know that. So, by the way, when was linear algebra made as a subject in mathematics? Now you are taught linear algebra from first year of college, and it's made the foundation of everything. Whether you studied multivariate calculus, then the total derivative is a linear map, or integral is a linear map, or whether you study field theory, so all the time it is linear basis, extensions, whatnot. So it looks like linear algebra is very, very fundamental. Differential equations use linear algebra. So linear algebra is a product of 1930s. Functional analysis is a product of 1920s or a bit earlier. Functional analysis came before linear algebra. Linear algebra came afterwards. So often these basic things get defined later as you systematize mathematics. So this rational equivalence and its preservation under proper morphisms had to wait for a correct definition of proper morphism, correct definition of subschemes, and all these definitions slowly came. Around 1945, the pace of making the right definitions had become very fast, and Grothendieck was already in Paris, and he hadn't yet contributed anything, but Chevalier was in great form and was leading all this effort at cleaning up algebraic geometry. André Weil had already done his stuff, and so Chevalier ran a seminar in 1945 on algebraic cycles and so on, and he defined Chow groups, and he gave a rigorous proof of this. So let's call it Chevalier's theorem. Okay? So we want to prove Chevalier's theorem, and so okay. So let's go on and talk a little bit more about this, because it's going to take our next 2 lectures to prove this. So let's make a slow start, make sure you understand everything. So if the image of Fv is W, if Fv is W, has dimension 1 less, okay, or 2 less than V. It is less, right? So it can be equal to, less than or equal to, it can be equal to dimension of V, it can be equal to dimension of V minus 1, it can be equal to dimension of V minus 2 or less. So the proof makes these cases. If the dimension of the image is 2 or less than 2 less or even smaller, how do I say it? I have already called dimension of V to be n plus 1, I think, right? So if the dimension of W is n minus 1 or smaller, then it's a triviality, showing that the Y divisor will go to 0. Why? Because the Y divisor is going to be made up of pieces which are n-dimensional. And that's already n minus 1 dimensional. So these pieces themselves are going to go to n minus 1 dimensional or less. Therefore, the direct image is going to be 0. So the y divisor is going to go to 0 at the level of cycles. You want to show rational equivalent to 0, go to rational equivalent to 0. But if the dimension is too small, rational equivalent to 0 goes physically equal to 0 as cycles. So of course rational equivalent to 0. So interesting cases are when the dimension is the same or one less. Okay? One less, what can happen is, I have this y divisor R, it is made up of pieces which are of dimension n. The image of all of V is of dimension n, and these pieces must surject on all of V with a non-zero degree. So then the direct image is not physically 0. Then there is work to be done to show that it is rationally equivalent to 0. Another case is W is the same dimension as V. And then these pieces of the divisor are one less here. Their image could well be one less there also, but of the same dimension. So again, it's not physically 0 cycle. So again, work to be done to show it is rationally equivalent to 0. So this easily falls into these three cases. One of them trivial, the other two increasingly non-trivial. So you understood this argument? So one of this is trivial case. Have I said it? Yes. So this is the trivial case. The non-trivial cases are these two. This one we'll treat first tomorrow, and then we'll treat one where the dimension goes down by 1. And what is the idea? When the dimension is the same, so a rational function whose y divisor I want to go to show to 0, that cycle I am going to show is the y divisor of a rational function on W. What rational function on W? So when I have finite extension of fields, is there a way of going from this larger field to the smaller field, which will take non-zero elements to non-zero elements? Yeah, is there a way? And that is the norm. And it's a multiplicative homomorphism as we want it to be. So if I have field extension, a finite extension of fields, in the reverse direction there is a norm map. Can somebody quickly remind me how norm map is defined for a field extension? Determinant. You take the determinant of the scalar multiplication map by something upstairs. Upstairs field is a finite dimensional vector space over the lower field. And you take this endomorphism defined by this scalar and take its determinant. And why does it take non-zero elements to non-zero elements? Because it's an injective map, you see. So its determinant has to be non-zero. If I take a non-zero scalar and multiply by that, what if I take the scalar from below? It will become a power. Why? Because the endomorphism matrix in any basis will look A. Okay? So that is the norm map. What happens to norm map in a tower of fields? Somebody boldly answer this. Composition. Yeah. Norm for a product. How does it do? You come by a norm from here to here and then again come by norm from here to here. That's the net effect of coming by norm from top to bottom. Composes. Okay, so you know enough about norm. And as we said, if I have proper surjective morphism of two varieties of the same dimension, then the function field extension is a finite extension. So there is a norm. And that norm I will name by those two varieties instead of those two fields. So I have this norm map, norm of V over W going from non-zero rational functions on V to non-zero rational functions on W. And what we will show is that when the dimensions are the same and I begin with the y divisor of a rational function, its direct image under this proper push forward is the norm of the push forward of the rational function. Y divisor of the norm of the rational function. So it's a norm of something non-zero. It's the y divisor of a non-zero rational function. Therefore, it is rationally equivalent to 0 by definition of rational equivalence. This is how we are going to prove that under this equal dimension case, it's getting well defined. Remember, these cases are about individual cycles. X and Y dimensions is a different story altogether. So all three cases may occur with respect to different varieties within that same X. There may be something which maps down to same dimensional, something else which maps down to one less, something else even smaller. Depending on that rational functions on them, these different cases are going to apply. So only after doing all these three cases will be able to say that yes, from Z lower star X to Z lower star Y, Zn X to Zn Y, rational goes to rational after doing these three cases. Okay? It's not as if we do one of those cases and then X to Y is certain dimension, we say, oh, we are done there. No. Because anything is possible for individuals of varieties. So that is going to be your approach when dimension of W is dimension of V. And that is the stuff for tomorrow, first stuff for tomorrow. And this was the last one. So now I'm going to go back and show you the list of slides. So this is the lecture we did. We talked of Chow groups and its relation to dimension, how and why it vanishes beyond the top dimension, how the top dimensional Chow group is such and such, etc. Then we talked of Chow group of an affine line. We have a complete answer here. Chow groups of affine space, we only determined the Chow group top one and the 0th one. Then we talked of Chow groups of projective line and we determined it completely. Then we talked of the degree of proper surjective morphism and the various avatars that degree presents itself in topology, set theoretic cardinality of fiber, field extension degree. If there is a polynomial involved in defining things, then the degree of that polynomial. Or if I have f upon g going from P1c to P1c, something to do with degree of f and g, which you have not yet told me exactly what, that's for the discussion hour. Yeah, so we understood degree from various points of view. And from homology perspective, it's going to be the multiplication map on the top singular homology group. Verify that. From the Dirac homology perspective, and so on. Okay? All these match. So that was degree. Then we talked of proper push forward of cycles in terms of degree, making the degree as the multiplier. And then we talked of proper push forward of cycles 2, means what, I don't know, meaning the thing spilled over into the next slide. And then for proving that this proper push forward descends to Chow groups, our main job is to show that it takes rationally equivalent to 0 cycles to rationally equivalent to 0 cycles. And rational equivalence is ultimately defined in terms of Weil divisors of rational functions on varieties of one dimension extra. So what happens to the Weil divisor of a rational function on just one single variety? That we talked about and we stated the answer, what happens. And now the job comes to proving it when the two varieties have the same dimension, then when it is one less, and when it is two less, we have already commented it's trivial. Okay, bye.